During the course of the past few videos, we've been looking at different probability distributions. In this final video in this sequence, we've got to make our own mind up about which distribution to use. So it's worth recalling the distributions that we've actually met. First one is we've met the discrete uniform distribution, and that is appropriate when we have a random variable that takes a finite number of values, each with the same probability. So the probabilities are uniform across all of the different possible values. We've also met the idea of the binomial distribution. If x is the number of successes in a sequence of n independent trials of a simple experiment, where there is a constant probability p of success in each go and a constant probability of 1 minus p of failure, then the probability distribution of x can be summarized as the probability that x equals r is ncr times p to the r times q, or 1 minus p, to the n minus r. And we've had the idea of a random variable. X is said to have the Poisson distribution with parameter lambda, where lambda is bigger than 0 if the probability that x equals r is lambda to the r over r factorial e to the minus lambda, where r can take any value from 0 upwards, any integer value from 0 upwards. And in particular, if we have x is the number of events that happen in, well, we've called it a time t, but we've seen also that it might be an area A instead, or in a weight m of muffins, how many chocolate chips we get in the muffins and so on. So that's why I put the word time in inverted commas. So if x is the number of events that happen in time t, and the events occur randomly and independently of each other, they occur one at a time, and that on average the events occur at a uniform rate. That is, the expected number of events in a given interval is k times the length of the interval. Then we may model x by the Poisson distribution with lambda equals k times t. So let's see this going into action with some examples. So in the garden of a keen gardener, weeds appear at an average of 1 weed in every 5 square meters of her garden. Find the probability that a flower bed of area 7 meters squared contains more than 1 weed. And then secondly, the gardener has 40 beds, each of 7 meters squared. A visitor inspects 6 of these beds chosen at random. Find the probability that exactly 2 of the flower beds inspected contain more than 1 weed. So, if we let x equal the number of weeds in an area of 7 meters squared, then x is going to be Poisson with lambda equals 1.4. Because we've been told that 1 weed in every 5 square meters, so in other words that's average rate of 0.2 weeds per square meter. So 0.2 times 7 gives me 1.4. So x is Poisson with lambda equals 1.4. So the probability that x is greater than 1 is going to be 1 minus the probability that x equals 0 or 1. So that's 1 minus the expression for the probability that x is 0 plus the expression for the probability that x equals 1, which we can calculate easily and obtain 0.4082. Now for part B, we've got a visitor who comes and inspects 6 of these beds chosen at random. Find the probability that exactly 2 of the flower beds inspected contains more than 1 weed. Well, we know that the probability that a bed contains more than one weed is 0.4082. And provided we have got independence of one flower bed from the next flower bed, then we will be able to say that the number of beds inspected with more than one weed would have the binomial distribution with n equals 6 and p equals 0.4082. So the probability that y equals 2 would be 6c2 times by 0.4082 squared times by 1 minus 0.4082 to the power 6, which comes out to be 0.307. We've got Mr. G walks to work with probability 0.35 and otherwise he drives to work. Miss H walks to work with probability 0.2 and otherwise she drives to work. Calculate the probability these two people travel to work by the same means on a randomly chosen day. What assumptions have you had to make? Well, the only way we're going to be able to handle this is to say, well, we want the probability they both walk or they both drive. We don't know how they're related to each other, so we're going to have to assume that the two people are independent to each other. So whether Mr. G walks or drives is independent of whether Miss H walks or drives. So we've got 0.35 times by 0.2 plus 0.65 times by 0.8, which gives me 0.59, that they both travel by the same means. So, and to get that answer, we had to assume that Mr. G's choice of transport was independent of Miss H's choice of transport. That may be quite a drastic assumption, because in all likelihood there might be a background factor like the weather affecting that choice, and it might well be that Mr. G and Miss H are likely to drive to work if the weather is poor. So they might well not be independent. Calculate the probability that these two people travel to work by the same means on at least 12 days in a period of 20 working days. What assumptions have we had to make? Well, assuming that our previous answer was correct and that each day is independent of the other days, then the number of days that they both travel by the same means is going to be a binomial distribution with n equals 20 and p equals 0.59. The probability that x is greater than or equal to 12 is 1 minus the probability that x is less than or equal to 11. We can use our calculators to get that, so that's 1 minus 0.4406. So that is 0.5594. And we have had to assume that independence from day to day. I'd like you to have a think about how reasonable you think those assumptions are. So he has two fair normal cubical dice, each with faces marked 1, 2, 3, 4, 5 and 6. One is coloured red and one is coloured blue. She throws the two dice and uses the scores to obtain three numbers. X is the score on the red dice plus the score on the blue dice. Y is the score on the red dice times by the score on the blue dice. Z is 7 times the score on the red dice plus the score on the blue dice. Which of these random variables has the discrete uniform distribution as its probability distribution? Explain your choice. Or we just need to try and have a look at what the possibilities are for each of these three scores. So for X, we've got an outcome space diagram that looks like that. And we can see here that we've got possible scores of 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. but they are certainly not got equal probabilities. For instance, we've got the probability that x equals 2 is 1/36. The probability x equals 3 is 2/36. So it cannot possibly be a discrete uniform distribution, because if it was, all the probabilities would have to be the same. The sample space diagram or outcome space diagram for y can be easily obtained as well. And again, we can see there are quite a number of possibilities here, but it's very quick and easy to see that, for instance, the probability that y equals 1 is 1/36. The probability y equals 2 is 2/36. And that's quite enough to say that y is not a discrete uniform distribution. If we look at the outcomes for z, we get that. And the critical thing here is you will see that we've got lots of different possibilities: 8, 9, 10, 11, 12, 13, 15, 16, 17, 18, 19, 20, 22, 23, 24, 25, 26, 27, etc. But there are no repetitions there. So we've got z takes 36 different values, each with probability 1/36. So that means that z has got the discrete uniform distribution. Right, for each of the following random variables, I want you to think which probability distribution, if there is one, is appropriate. Give full details and if possible, and state any assumptions you needed to use that particular probability distribution. So pause your video at this stage and just work through these different examples. Are they binomial? Are they Poisson? Are they discrete uniform distribution? Are they none of those? If you are going to use one of the standard distributions, do you have to make any assumptions? So have a think about that. Write your answers down on a piece of paper and take them along to your next lesson. So that finishes our look at the process, or trying to get us to think about the selection of suitable probability distributions.